All right, so I want to start in section 2.1, and there are really only two small topics out of this whole section that we're supposed to cover per the department syllabus, which is the distance formula and the midpoint formula. You've probably seen these before, so hopefully this is just a quick review. All right, so starting with the distance formula, to find the distance between 2 points on the coordinate plane. And the first key is that a distance, by definition, cannot be a negative quantity. It can only be either positive or 0 if they're the same point, right? So, for example, if I pick 2 points on the plane such as -3, 1, and -3, 3, okay, and go ahead and graph those 2 points. So -3, 1 is here, -3, 3 is here, okay. So it's easy by inspection, because they're on a straight line, to see that the distance between those 2 points is 2, okay? So what, however, if we had 2 different points, let's say in this case 2, 2 and 5, 3, okay, and again go ahead and plot those 2 points. So 2, 2 is here, 5, 3 is here. All right, so now in this case, sorry, that's not exactly a straight line, but I did my best. It's not as clear what the distance is there, okay? But what we can do is use that straight-ish line as the hypotenuse of a right triangle. So let's say if we turn this into a right triangle, like this and this, okay, then I'm sure everybody remembers the Pythagorean theorem, which only applies for right triangle, which says that a squared plus b squared, and a and b are the 2 legs, is equal to c squared, where c is the hypotenuse. Okay, so in this case, this would be one leg, let's call it A, and that distance is clearly equal to 3. This would be B, the other leg. This distance is clearly equal to 1. And then this is the unknown distance, the distance between the 2 points, and we call that C. So in other words, 3 squared plus 1 squared equals C squared. 3 squared is 9, plus 1 squared is 1, is 10. So 10 is equal to C squared, and then just take the square root of both sides. So therefore, C, that distance that we're looking for between the 2 points, is equal to the positive square root of 10. You know, normally when you use the square root property and take the square root of both sides of an equation like we just did, you have to apply a plus or minus in front of the solution like this. In this case, we're specifically finding a distance, so we know that it can't be negative. So in other words, C is equal to the square root of 10. That's the distance between those 2 points. So what we just did there with the Pythagorean theorem is exactly what the distance formula does for us. Okay, I'm going to scooch up and erase all this stuff. Okay. So let's say we have 2 points. We'll call this one P, and we'll call this one Q. Okay. And let's give coordinates to these points. So in other words, the point P is the coordinates x1 and y1, and the point Q is coordinates x2 and y2. So, in other words, like right here, if you drop a line down from P, that value is x1. If you drop a line down from point Q, this value is x2. Sorry, that's supposed to be an x. If I can make this a little thinner, I probably can, but I'm not sure how. Okay, so what that means is that this length, this side of the right triangle, is equal to x2 minus x1. Okay, and similarly, this leg of the right triangle is equal to y2 minus y1. Okay, and again, the whole point is we want to find the length of the hypotenuse, which we will call C. Okay, and as we know, the length of this side squared plus the length of this side squared equals the hypotenuse squared. So if we write that out, we get x2 minus x1 quantity squared plus this side squared, y2 minus y1 quantity squared is equal to c squared. Okay, and then what we want is to solve for c equals what? So to do that, we just have to take the square root of both sides of the equation. The square root of c squared would be c, and that would equal the square root of all this stuff on this side. So that is basically how you derive the distance formula, which is given in this section of the book. Let me scooch down and erase again. So pause if you need to. Oops. All right, so formally from the book, there's the equation for the distance formula. And then just to have you guys just go ahead and pause this for a second really quick. And you go ahead and use the distance formula to find the distance between these 2 points. And it doesn't matter which one is P and which one is Q, just label the first one, say x1 and y1, and the second, x1, y1, and the second one x2, y2. So go ahead and pause this for a second and calculate the distance. Okay. So if we're using the distance formula, we're going to go distance is equal to the square root of, okay, so x2 is -4 minus 1 quantity squared plus, okay, y2 is 3, and then minus a -2. Be careful with your negative signs there. Quantity squared. Okay. So that's going to be the square root of, so -4 minus 1 would be -5. -5 squared is 25. And then plus 3 minus a -2, it turns into 3 plus 2. So that's again 5 squared, so 25. All right, so square root of 50 seems easy enough that we're done, but don't forget that you have to always simplify your radical expressions as far as possible. And 50, of course, is 2 times 25. So in other words, this is the square root of 25 times 2. Okay, and 25 is equal to 5 times 5. So in other words, we can take the square root of 25 and pull that out from under the radical. So the final form here would be that this is equal to 5 times the square root of 2. All right, I'm going to scooch this down and erase everything, so pause if you need to. And let's go on to the second quick topic in this section, which is the midpoint formula. The midpoint of a line segment is the point, I'm not going to write this out, I'm just going to say it. It's the point halfway between the two endpoints. Halfway between the two endpoints. So again, to start with a really easy example, if I have one point which is negative 4, 4, if I have a second point which is 6, 4, and we can go ahead and sketch that. So negative 4, 4, 6, 4. So if those are the two endpoints, then the segment connects those two. And then just by inspection, we can see that the length of this segment is 10 units. So halfway in between it would be 5 units, right? So that would be this point right here, okay? And so the midpoint would be the point 1, 4. So that was pretty easy to do intuitively. Basically, you know, the y coordinate remains the same. The x coordinate, we basically just averaged the two x coordinates. We had negative 4 and 6, and we basically just averaged them. We took negative 4 plus 6, which would be positive 2. We averaged them, divided by 2 is equal to 1. Okay, so that's how we got that midpoint coordinate, by averaging the two x coordinates. So that's how the midpoint formula works. You just average the x coordinates of the 2 points, you average the y coordinates of the 2 points, and that will give you the midpoint of the line segment. Okay, I'm going to scooch down. Okay, so there formally is the midpoint formula from the book. You guys go ahead and do this one. Okay, so here's one point, here's the second point. Go ahead and plot them and connect the line segment, and then use the midpoint formula to calculate the midpoint. And then you can just use your rough sketch to make sure that you're about right. Okay, so go ahead and pause this for a second and do that. All right, so the midpoint of the x values would be 3 plus negative 5 divided by 2. So that's negative 2 divided by 2, which would be negative 1. The midpoint of the y values would be 6 plus 1 divided by 2. So that's 7 divided by 2, 7 halves, or in other words, 3.5. And we can also just check that. So the point 36 is here. The point negative 51 is here. Our midpoint allegedly is at negative 1, 3.5. So if we go ahead and plot that one, negative 1, 1, 2, 3.5, yeah, just by inspection, oops, I totally missed that, but you know what I mean. So yeah, that midpoint looks correct. Okay, let me resume. I'm on section 2.2 now. And again, there's only a few things we want to look at. We want to look at symmetry of equations. We want to look at intercepts of equations and equations of circles and graphs of circles. All right, so let's start with the symmetry. And there's three types of symmetry that we are going to look at. Symmetry with respect to the y-axis, symmetry with respect to the x-axis, and symmetry with respect to the origin, which of course is the point 0, 0, the origin. Okay, and I think, you know, everyone knows intuitively what symmetry or being symmetric means. It means that something, in this case a graph, is the same on both sides, or that one side is a mirror image of the other. Okay, so basically these three types of symmetry are different only in where we place the mirror to create the symmetry. So let's start with symmetry with respect to the y-axis. And as an example, the function y equals x squared. Okay, this is a quadratic function. And in this case, the graph is a mirror image over the y-axis. Okay, of course, this is the y-axis. And if you were to fold the paper in half over the y-axis, these two halves of the graph would lie on top of each other. Okay, and notice specifically for every point x comma y, there is an opposite point, negative x comma y, or opposite of x comma y, I should say. Okay, so for example, there is a point on this graph 2, 4. Okay, that's right here. And then if you were to fold that over the y-axis, there is also a point negative 2, 4. Okay, so that's the point right here. And, you know, a property of this is that these 2 points will always be the same distance from the y-axis. Okay. I mean, if you were to draw a line from here and here, you can see that's the same distance as the axis to this point. Okay. Now, this next definition isn't brought up until later in the chapter, but I'll go ahead and mention it now. If a function is symmetric with respect to the y-axis, it is known as an even function. Okay, an even function. So that's important to remember. That will come up again later. All right, I'm going to scooch down and erase. Okay. So that was pretty easy to determine that it was symmetric just by looking at the graph. If, say, we didn't have a graph of the equation and we just wanted to perform an analytic or by hand analysis to test for symmetry with respect to the y-axis, this is what you would do. You would take the equation, you would replace x with the opposite of x in the equation, you would simplify it. If the result that you get from doing that is equivalent to the original equation, that indicates that, yes, the graph is symmetric with respect to the y-axis, because it doesn't matter if you start with x or negative x, you still end up with the same output of y. So doing that here, here's the original equation. If I substitute the x with a negative x, so in other words, I want to do quantity negative x squared. Okay, and remember that means negative x times negative x, and of course the negative times the negative turns it back into a positive, so this ends up just being x squared, and then we say yes, that is the same as what we started with. So therefore, we can conclude, yes, it is symmetric with respect to the y-axis. Okay, moving on, symmetry with respect to the x-axis. I'm going to move this down again. Okay, so an example here. The equation y squared equals x, or you could also think of that as x equals y squared. If you were to plot that, this is what it would look like. So in this case, the graph is a mirror image over the x-axis. If you were to take this and fold it in half over the x-axis, the two halves of the graph would lay right on top of each other. Okay. In this case, for every point x comma y, there is a symmetric point x comma negative y. Okay, so for example, on this graph, we have a point 4 comma 2. Okay, so that's right here. And there is also a point 4 comma negative 2. And as before, these 2 points will always be the same distance from the x-axis this time. If we didn't have a graph of the equation and we wanted to analytically determine if an equation is symmetric with respect to the x-axis, in this case, replace y with negative y in the equation, simplify it. If it's equivalent, yes, it is symmetric, because it doesn't matter if you have y or negative y, the equation is going to be the same. So doing exactly the same thing before, in this case we're going to replace this with negative y, quantity squared is equal to x. If I simplify the left-hand side, again, that means negative y times negative y, which simplifies to y squared equals x. And again, yes, that is the same as what we started with. So we can conclude that it is symmetric with respect to the x-axis. Okay. All right, I'm going to move on to the next page. Symmetry with respect to the origin. So here is an example, the cubic equation, y equals x cubed. In this case, the graph is a mirror image over the origin. Now this one is, I think, harder to visualize. So let me just tell you this first. In this case, for every point x comma y, there is a symmetric point negative x comma negative y. So specifically, for example, we have a point 1 comma 1, which is right here. And symmetrically, there is a point negative 1 comma negative 1. Okay. The 2 points are always the same distance from the origin. And because it's not as easy as just, say, folding it over the x-axis or folding it over the y-axis, I always think of it in terms of, well, if I go this way a certain distance over and up, then the symmetric point is going to be, do the opposite of that. Go back and then down. Okay. All right, if a function is symmetric with respect to the origin, it is known as an odd function. An odd function, okay? So remember above, if it was symmetric with respect to the y-axis, it was even. Now we're saying if it's symmetric with respect to the origin, it's odd. And if you recall, we didn't give a particular name to something that was symmetric with respect to the x-axis. Here, let me just come back here. Okay, and does anybody know why this doesn't have a particular name? The reason is that this is not a function. And we'll go over this later in the chapter, but it fails the vertical line test. It intersects in more than one point. Okay, it's not even a function, therefore we don't even bother giving it a special name. Okay. All right, so coming back to here, to determine this analytically, replace x with negative x and replace y with negative y in the equation. After you simplify, if the result is equivalent, then yes, the graph is symmetric with respect to the origin. So in other words, I'm going to replace this with negative y. I'm going to replace this with negative x, okay, quantity cubed, which means negative x times negative x times negative x. Okay, so 3 negatives indicates that the result is still going to be negative. And then we've got an x cubed. So now we have a negative y equals a negative x cubed. And basically at that point, if you just multiply both sides of the equation by -1, okay, so then we end up with y equals x cubed, which, yes, is what we started with. So yes, we know that it is symmetric with respect to the origin. Okay, I'm going to scooch and erase. All right, so what I want you guys to do at this point is pause. I want you to take each of these two equations, test them for symmetry with respect to the x-axis, the y-axis, and the origin. All right, so just go ahead and pause the recording and test each of these. Okay, remember when we test for y-axis symmetry, we replace x with negative x. So in other words, I'm going to have y equals 2 times negative x quantity cubed minus 4 times negative x. So this is going to simplify to y equals, so negative x quantity cubed is going to be negative x cubed. So this is going to end up being negative 2x cubed. And this is minus times a minus, so this will end up being plus 4x. Okay. So if we compare that to the original equation, no, it's not the same. So it is not symmetric with respect to the x-axis, the y-axis. Test it for x-axis symmetry. This time we replace y with negative y. So in other words, negative y equals, and then the other side remains the same, 2x cubed minus 4x. If I multiply the whole equation by -1, I end up with y equals negative 2x cubed plus 4x. And then if we compare that to the original equation, nope, it's not the same. Okay, so it's not symmetric with that. Test it for the origin, replace both x and y. So I'm going to have negative y equals 2 times quantity negative x cubed minus 4 times negative x. Negative y equals negative 2x cubed plus 4x. Multiply the entire equation by negative 1, which means multiply every term by negative 1. So then y equals 2x cubed minus 4x. Okay, and if we compare that to the original equation, yes, that is the same. Okay, so in other words, this is symmetric with respect to the origin. Okay, so then just a note that because this is symmetric with respect to the origin, that this would be an odd function. And let's just go ahead and plot it. Okay, so this is 2x cubed minus 4x. All right, so there you go. You can see, you know, kind of like I said before, if you think of it as, you know, if you go over and in this case down, okay, then that is equivalent to doing the opposite. In this case, go back and up, and there's the symmetric point. Okay. All right, so let's look at the next one. X squared plus y squared equals 25. Test it for the y-axis symmetry by replacing x with negative x. In this case, if I do negative x quantity squared, okay, we can already see if we do negative x quantity squared, that's going to be negative x times negative x, which is going to simplify to x squared plus y squared equals 25, which is the same as what we started with. Okay, so yes, it's symmetric with respect to the y-axis. X-axis symmetry, in this case, we're going to replace y with negative y. Okay, so negative y quantity squared. And already we can see negative y times negative y is going to simplify to y squared equals 25. Okay, so yes, it's symmetric with respect to the x-axis. Origin, replace both, and you can probably already see, even if I replace both, okay, and then plus quantity negative y squared, both of those are going to simplify to x squared plus y squared equals 25. Okay, so yes, it is symmetric with respect to the origin. Okay, so let me pull the grapher back up and we'll plot that one. X squared plus y squared equals 25. Let's just clear this. X squared plus y squared equals 25. Okay, so you can see it's a circle, and that's what we're going to talk about next. And yeah, no matter which way you fold it, x-axis, y-axis, or if you do the over and up and back and down, you can see that it is symmetric with respect to all three of those. However, it is not either an even or odd function because, again, it's not a function at all because it fails to pass the vertical line test. All right, so let's go on to finding intercepts. And I'm confident that you already know how to find the intercepts of a graph. I know that you had to learn how to do this in algebra. You can use the same method that you did for finding intercepts of a line to find intercepts of other types of equations. Okay, so here's just a good graph from the book just to kind of remind you what the intercepts are. So the y-intercept, which is right here, okay, is where the graph crosses the y-axis. And the x-intercept, in this case, which is right here, is where the graph crosses the x-axis. Okay, so that's all pretty self-explanatory. Now, we're going to talk about the difference between just an equation versus a function, okay? A graph of a function can have more than one x-intercepts, okay? So, for example, I could take this graph, and if I extended it, maybe it goes down for a bit, but then maybe it comes back up like that, in which case I could have, say, another x-intercept. In fact, it could keep going back and forth, and I could have many x-intercepts, okay? So it can actually have an infinite number of x-intercepts. Okay. However, how many y-intercepts can a function have? It can only have exactly one. Okay. Because if it intercepted the y-axis in more than one place, like if this came up here and did this, okay, now it is no longer a function, okay, because again, it fails that vertical line test. And we'll talk about that again briefly later in the chapter, okay? So there is a difference between a function and an equation. An equation, you can have any number, say infinite number of x-intercepts. You can have any number, say infinite number of y-intercepts, if it's just any old equation, okay? Okay, so specifically finding the intercepts of an equation, if you want to find the x-intercepts of an equation, then you need to set y equal to 0. Because if you look back up here at the graph, at the x-intercept, the y-coordinate is 0. Similarly, to find the y-intercepts, set x equal to 0. Because, you know, when the graph passes through the y-axis, that means that the x-coordinate is 0. All right, I'm going to erase and scooch down. Let's look at an example. Find the x and y intercepts of the graph of this equation. X equals y squared minus 5y plus 6. So, to find the x-intercept, which again means set y equal to 0. So in other words, x equals, I'm going to set this equal to 0. So in other words, 0 squared minus 5 times 0 plus 6. So that's pretty easy because this is 0 minus 0 plus 6, so it just equals 6. So in other words, the x-intercept is the point 6, 0. And let's go ahead and mark that on the graph. That would be right here. Okay. Find the y-intercept. Set x equal to 0. Okay, so in other words, coming up here, I'm going to set x equal to 0. 0 equals y squared minus 5y plus 6. And then we need to solve that. It's a quadratic in terms of y. And we want to see, can we factor that? Yes, we can, because it would be y minus 2 times y minus 3. And then using the zero product property, the solutions would be either y equals 2 or y equals 3, which means there's actually 2 y-intercepts, the points 0, 2 and the points 0, 3. Okay, so 0, 2 and 0, 3. And then I don't know if you can tell, just from the equation, but this is like a quadratic, but it's for x in terms of y. It's like the opposite. So generally, this graph is going to do something, okay, this is a terrible graph, kind of like this. Okay. So yeah, it's not a function, but it's an equation, and we found the intercepts. All right, I'm going to go on to the next page. Circles. Okay. All right, there's nothing tricky about circles, really. You're probably just not as familiar with equations of circles, maybe, as you are for equations of lines. So specifically, there's a definition of a circle: the set of all points that are a fixed distance r from a certain point h, k. Okay, so that specifically is your center point right here. So your center is h, k. This is just the convention using these particular letters. And then the radius of the circle is r. So the distance from the center out to a point on the edge of the circle, that is r, the radius. Okay. So now we already know the distance formula. And once we know the distance formula, it's pretty easy to derive the equation for a circle. Okay. So we know the distance between any 2 points. Okay, so if we pick any point on the circle itself, we'll call it point P here with coordinates x, y. Okay, and then if we want to use the distance formula to find the distance from any point from the center h, k, then we would say the distance, just using this formula, is equal to the square root of the quantity x minus h, quantity squared, plus y minus k, quantity squared. And of course, we've already called that distance something. It's equal to the radius, r. Okay? So in other words, r is equal to all this stuff. And then the only other thing is, instead of leaving the equation with a big giant radical with all this stuff under here, is what we typically do then is just square both sides of the equation. So I'm going to square this side, I'm going to square this side, and then we're going to rewrite the equation after we've done that, and we're going to end up with x minus h, quantity squared, plus y minus k, quantity squared, is equal to r squared. Okay, so specifically, This form of the equation is known as the standard form of the equation of a circle, and it's also called the center radius form. The reason it's called the center radius form is because you can read off the center, the point h comma k, and you can also read off the radius. All right, I'm going to go to the next page and look at an example. All right, so given this equation, okay, so and just remember this represents x minus h, quantity squared. This represents y minus k, quantity squared. This represents r squared. So from the equation, I can see that h equals 2. I can see that k equals not 4, but negative 4. Okay? Because when I have y plus 4, that's the same as y minus a minus 4. Okay? And the minus sign is built into the equation for the circle. Okay? And then I can therefore say that the center of the circle is going to be at the point 2 comma negative 4. All right, we can go ahead and plot that. So 2 negative 4 is like here. R squared is equal to 16, therefore r is the square root of that, which is 4. Okay, and that's basically all you need to plot a circle. From the center point, just kind of count out in the 4 directions, go 4 units. So like I'm going to go 4 up, 1, 2, 3, 4. There's a point. I'm going to go over 1, 2, 3, 4. There's a point. Down 1, 2, 3, 4. And left 1, 2, 3, 4. Okay. And then basically just kind of reasonably approximate the circle. And I could have done better, but not too bad. Okay. Now, specifically, if your circle is centered at the origin, the point 0, 0, then your standard equation reduces to simply x squared plus y squared equals r squared. Okay? Because both h and k are equal to 0. All right, so when you do x minus h or x minus 0, it just reduces to x and so forth. So for example, x squared plus y squared is 9 is just we just know by looking at that is a circle. It is centered at the point 0, 0, and it has a radius of 3. All right, and if we wanted, we could go up to the same grid. We could say the center is here, the radius is here, so here, so here, and here. Okay, so basically like that. All right, so we like the standard form of the equation of a circle. It's useful because you can read off the center and you can also just read off the radius. All right, it's very easy to just look at the equation and be able to plot it. Okay. However, the equation of a circle can also be written in another form, which is called the general form. Okay, and so the general form, let me just scooch up and erase. The general form is written as follows: x squared plus y squared plus ax, okay, where a is just some constant, plus by, again a constant, plus c, a constant, equals 0. So, for example, if we take the equation of the problem we just did, we could, and remember, the form that we started with is standard form. But what we could do is just multiply this out and therefore end up with general form. So, in other words, x minus 2 squared means x minus 2 times x minus 2. Okay, and if you just FOIL that out, then you get x squared minus 4x plus 4. Same thing with the y plus 4 squared. That means y plus 4 times y plus 4. FOIL that out. Okay, so then you would have plus y squared plus 8y plus 16. And that all equals 16. So now we have all the individual terms. We just want to put them so they look like this. So we want the x squared term first, so that would be x squared. And then the y squared term, so plus y squared. And then the x term, so minus 4x. And then the y term, so plus 8y. And then we want to gather up all the constants. So if I subtract 16 from both sides, that basically cancels out this, and then I'm just left with a plus 4. Equals 0. Okay. So that is the general form. Okay, it's equivalent to the standard form. Okay. And just a couple notes, it's not really as useful. You know, by looking at that general form, we can't tell what the center or the radius is. And also, just to note that your coefficient on your x squared and y squared term should always equal 1. If it is equal to something other than 1, then you need to just divide it out of the entire equation. Okay. All right, so it's pretty easy to go from standard form to general form. That's what we just did. But it's a little harder to go from general form to standard form. Okay. So, and in particular, we're going to do this by using a specific technique, which is called completing the square. Okay, completing the square. You've probably heard that before from algebra, which basically means creating a perfect square trinomial. Okay, so in other words, a perfect square trinomial, for example, is something like x squared minus 4x plus 4, because that is equal to the quantity x minus 2 squared. So that is known as a perfect square trinomial. So let's look at an example. Find the center and radius of this circle. All right. So this circle is given in general form. We want to convert it to standard form. So we want to start by grouping the x terms, and then grouping the y terms, and then basically moving the constant to the right-hand side, RHS, right-hand side of the equation. Okay. So if we start by doing all of that, so I want to group my x terms. I've got an x squared plus 4x. So I'm going to have x squared plus 4x. And then I'm going to purposely leave some space here. Then I'm going to group my y terms. So my y terms, I've got y squared and 10y. So plus y squared and then plus 10y. And then again, I'm going to purposely leave a little space. And I'm going to take the constant and move it to the other side. So just subtract 15 from both sides, so equals negative 15. All right, so to complete the squares, for example, start with the x term. Take half of the x term coefficient. The x term coefficient is 4. So half of that is 2. Square it. Okay? 2 squared is equal to 4. Add it to both sides. So I'm going to, right here, I'm going to add 4. If I add 4 to this side of the equation, then I have to add 4 to this side of the equation. Okay? Now, do the same thing for the y terms. So I'm going to take half of the y term coefficient, which would be 5. I'm going to square it, which is 25, and I'm going to add that to both sides of the equation. 25. If I add 25 here, I have to add 25 over here. Okay? And the whole reason we're doing this is because by doing that, we have just created a perfect square trinomial here and a perfect square trinomial here. Okay? So what we end up with then, this x squared plus 4x plus 4 factors as x plus 2 quantity squared. This y squared plus 10y plus 25 factors as y plus 5 quantity squared. And then on the other side, 25 minus 15 is 10 plus 4 is 14. Okay? All right, I gotta scooch this down just a little, see what's down here. I guess nothing else. That must be a typo. All right, but anyway, the point is now we have this in the correct form, and we can read off the center of the circle, and the center would be -2, -5. And we can read off the radius, which would be the square root of 14. And then if you wanted to actually plot this, just do the square root of 14 on your calculator. It's about 3.7. So you could make an estimated plot just by doing that. All right, now I'm going to scooch down and erase. Okay, so again, I want you guys to pause and go ahead and try these two problems on your own before you watch the solution. All right, so number 1, write the standard form of the equation with the center and this radius and graph it. All right, so again, standard form means we want to do x minus h quantity squared plus y minus k quantity squared equals r squared. All right, so this is h, this is k, and this is r, square root of 5. So if we basically just substitute those values in, Here, when I do x minus minus 5, it turns into x plus 5 squared, and then plus y minus 3 squared equals r squared. So the square root of 5 squared is 5. All right, and so to plot this, let's just go to the center, which is at -5, 3 right here. And then we know the radius is the square root of 5. And if you just do that on your calculator, that is approximately equal to 2.2. Okay. So from this center, just go about 2.2 in all 4 directions. So that would be, you know, about here, about here, about here, and about here. Okay, and then just, oops, kind of missed on that side, draw your circle. Sort of like that. All right, number 2, we've got the general form, and we need to transform it into standard form so that we can read the center and the radius. All right, so kind of like we did before, we're going to group the x terms, x squared minus 6x, and then I'm going to leave some space, and then plus y squared plus 2y, and then I'm going to leave some space, and then I'm going to move the constants, or constant in this case, to the other side. Subtract 9 from both sides, so it would be -9. All right, and then I need to complete the square in both cases. Okay, so in this case, if I take half of -6, that would be -3. Quantity squared would be +9. So I'm going to add 9 to both sides. And for the y terms, I'm going to take half of 2, which is 1, and square it, add it to both sides, so that's just 1 plus 1. All right, so now we've completed the square, and we can write these in factored form. So in other words, x minus 3 quantity squared plus, this would be y plus 1 quantity squared, and then equals 1. So from here we can read off the center, which is going to be the point 3, -1. And then we can read off the radius. The square root of 1 is 1. So we can come over here and graph it. The point 3, -1 is the center. The radius is 1, so that's here, 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 and here. All right. Okay, and just a comment that I am going to skip section 2.3 because that is all about lines, and you should know about lines from taking algebra. You're welcome to review it yourself. But when I resume in class, I'm going to start right on section 2.4.